All right, let's look at the integral test. All right, so we assume that the term is decreasing and non-negative. All right, so summation n goes from 1 to infinity of an. All right, converges if and only if. So this is my lazy notation for if and only if. Right, the improper integral from 1 to infinity f of x dx, where f of x matches the value of an at every integer, right? So the if and only if means that if the series converges, corresponding integral converges, and also if the integral converges, then its corresponding series converges. So they converge and diverge together, right? So let's try to prove this guy. All right, so this is actually pretty easy to see once we can draw a picture, right? So let's say you have f. Graph of f looks like this. And let's visualize the summation of an, so a1 plus a2, by the sum of the areas of rectangles. Right? So I'm going to draw a rectangle like this. Right? So you have, I'm going to look at the, so here, this is going to be f of 1, which is the same value as a1. So I'm going to use this a1 as the height to create a rectangle with base 1. So this area is going to be A1, right? So if you go to add 2, so the height is A2 here, then I'm going to draw a rectangle like this. This is A2, right? So this is at 3, so this is going to be A3, right? So you can see that sum of A1, A2, A3, that's going to give you the series we're talking about. So summation n goes from 1 to infinity of an. Right? Then if you compare that region with this area under the curve of f of x from 1 to infinity. So the integral represents this region right here. Right? And you can visually see that the sum of the, A1, A2, A3 is going to be larger because you have a little extra here, little extra here, little extra here than the integral. So we know that here we have an integral from 1 to infinity f of x dx is going to be less than or equal to the series. Right? And if you draw it slightly differently, we can get a different inequality. So I'm going to use A1. So this is still A1. And I'm going to actually draw a rectangle this way. Right? So this is going to be A1. Right? Then here, we're going to draw it this way. So that's going to be A2. Right? Then this is going to be here. Integral here, then you have that. So this is going to be A3, right? Then we're going to add those guys up so you get the series here, right? If you compare that with, this is a little bit strange, but we're going to compare that with, right? I'm going to keep A1 right here and combine that with the region under the graph of f from 1 to infinity. So we're talking about those guys. Right? So which is, so we keep A1 and along with the area of the region from 1 to infinity, right? So f of x dx, right? So you can see that A1 plus the integral is going to cover a little bit more. You can see that this is a little extra here and there's a little extra there. So we know that this is going to be larger or equal to the series there. Alright, so using this integral, we can make this conclusion. Right? So if summation, right, the series, right, converges, right, using here this inequality, by comparison test, right? By comparison, if this converges to a finite number, right, this integral is even smaller, so we know that the integral converges. So integral, so proper integral, improper integral I should say, converges, right? But if integral converges, then using this second inequality to show, alright, so if the integral is finite, then the series is also finite because it's smaller. So you have, because it's smaller here, n goes from 1 to infinity, an also converges. Right? So this is from inequality number 2. Right? So you can see that the integral or the series converges together, or they diverge together. So a series converges if and only if the corresponding integral converges. Right? So this is called the integral test. So if you want to know the convergence of the series, you look at the corresponding improper integral, which hopefully we can evaluate. Then if improper integral converges, then the original series is convergent. And if the improper integral diverges, then the original series also diverges. Alright, so let's look at a simple example. Let's look at the harmonic series because we already know the answer. Right, harmonic series is divergent. But let's try to show that using an integral test. Alright, so the corresponding integral would be integral from 1 to infinity. And all you have to do is, change 1 over n to 1 over x if you want. So here, right, dx. All right, so this is an improper integral, so we have to turn it into a limit. So limit, the upper limit t goes to infinity. So we have an integral from 1 to t, 1 over x with respect to x. All right, so this is going to be a limit as t approaches infinity, right? So antiderivative of 1 over x is natural log of absolute value of x. Then you're going from 1 to t, right? Then we still have to take the limit, but leave this guy alone for now. I plug in t, so you're going to have natural log of absolute value of t minus natural log of absolute value of 1. Right? But natural log of 1 is 0, so this guy is actually 0. And the t is going to infinity, so you can see that the natural log of infinity is infinity, so this guy actually goes to infinity, which means that this is going to be, so this improper integral is divergent, right? Therefore, harmonic series is also divergent, right? That's how we use the integral test. So just look at the convergence of the corresponding integral, improper integral. We can determine the convergence of the original series. All right, that's it. I hope that this was clear.